Right, so moving on to the tutorial number 10 now, regarding deflections. I've got the solutions all worked out for you, and I know there'll be members of the audience for these audio series saying to me, "Oh, well, could you actually give us more problems?" Well, what I'm telling you is change some of the numbers in a small way and do the problem yourself. Try and remember how to do it without slavishly following these tutorial audio solutions, and then you will learn how to do it. Giving you a wide variety of things might just confuse you. So just change the numbers slightly and try and remember how to do it yourself. As I've said before, repetition is important. Right, so the first question that we're going to deal with: a timber beam 85 millimeters wide by 295 deep, 4.5 meter span, carries a central point load of 15 kilonewtons. Calculate the maximum deflection if the E for timber is 12,000 newtons per square millimeter, or 12 kilonewtons per square millimeter. So there our beam is, 4.5 meter span. M is WL over 4. WL over 4. We do this again as we've just been doing in the lecture previously. WL over 4 by L over 2 by a half gives you the area of that triangle, times 2/3 of L over 2. 2/3 of L over 2 gets you back to the formula that we found earlier in the lecture, WL cubed over 48 EI. So it's purely a simple arithmetic problem of working out what the moment of inertia for this timber beam is, BD cubed over 12, and you've got the dimensions of the beam of 85 millimeter wide, 295 millimeters deep. You do pop it into BD cubed over 12, and you'll find that it is 181.845 times 10 to the 6th millimeters to the 4th, not cubed, millimeters to the 4th. I apologize there, but I'm glad I've had the opportunity to fix that. So, taking this into account, then we're going to substitute the inertia and everything into this formula that we've got. So we've got W, which is 15 kilonewtons, bring it to newtons, 10 to the power of 3. The span, WL cubed, span is 4,500 millimeters, or 4.5 meters, all cubed, divided by 48 EI, 48 times 12 times 10 cubed, which is your Young's modulus or elastic modulus, times the moment of inertia, which you've worked out. And when you do the simple arithmetic on your calculator, you'll find that that beam, that timber beam in the center, under that loading, deflects 13 millimeters. In other words, at this point it sags, there it sags 13 millimeters. So that is pretty straightforward and painless. I'm sure you all agree with me. Getting on to question, there's a bit of a mix-up here. We've got question number 1 and then we've got question number 4. Anyway, let's get on with number 4, then it doesn't matter in what order we've got them. Question number 4 says, a 410 UB 53.7 is used as a cantilever 3.5 meters in length. What point load can the cantilever carry at its free end if the deflection is limited to 10 millimeters? That's pretty straightforward from what you've learned so far. You actually substitute the deflection into the equation and then work out what the load is. Simple as that. So if you go through your tables and look up your one steel tables, you can work out, you can have a look at what the moment of inertia is for a 410 universal beam, 53.7 kilograms per meter. The inertia is 188 times 10 to the 6 millimeters to the 4th. I shall do that for those who are a bit unclear on this. Just let me grab my tables. Universal beam 41053.7, 41053.7. There it is there. So if you look up 360 UB 44.7, your moment of inertia is 188 times 10 to the 6 millimeters to the fourth. There it is there. Okay. You should all be able to look up those sorts of things now. E for the steel is given to you 210 times 10 cubed Newton millimeters. And the deflection is limited to 10 millimeters. Now, you can work out from first principles, or you could just substitute that formula that you've already done. But I would suggest you keep practicing by working it out from first principles. And the deflection at the free end on this cantilever there is WL cubed over 3EI. Now, delta is 10 millimeters. So your deflection, which is what you're normally looking for, but it's been stipulated, is 10 millimeters. What you're looking for is W. Span is 3.5 meters, 3,500 cubed, over 3EI. So, putting W out on the left-hand end there and rearranging the equation, you actually solve that and find that the actual load is 27,625 newtons, or 27.625 kilonewtons. Pretty straightforward. Question number 2 now. Sorry, they're not quite in order, but I'm sure that doesn't really matter to you. Question number 2. An encaustre timber beam has a span of 5 meters. It carries a central point load of 5 kilonewtons. There you are. 5 kilonewtons. If the breadth of the beam is 1/3 of the depth and the deflection is limited to 1/330th of the span, calculate the beam's dimensions. This is one of the trickier ones, but it's well worth knowing. Now, when we talk about an encaustre beam, it means it's fixed at both ends like that. It's not simply supported. And when you put the load on it, if these two fingers of mine were at the center of the beam and this was the encaustre support, you get that sort of profile, that sort of bending, because it's held firmly at the ends. That's what this diagram shows. 5 meter span. We've got to actually find out what this size of the timber beam is. Now, the fixed end moments for a beam that is built in on both ends, and you can look these up on tables, you could even look them up on YouTube if you wanted to. The fixed end moments there happen to be WL over 8, little WL over 8, okay? Oh, sorry, not little w, big W, because of the central point load, so it's a big W. Big WL over 8 is the fixed end moment, the moment generated at the support when you put the load on it. Because this thing actually, how does it deflect? It deflects like this. Because it's fixed at that end, it deflects like this. Like that. And your deflection is there at the center. And that's what we're going to work out for a fixed end, a beam with the fixed ends. So you can draw your moment diagram, and the fixed end moments are WL over 8, WL over 8 there. Something that you haven't come across previously is that you can superimpose your WL over 4 on this. As a matter of interest, this moment there, your free moment, is WL over 4. There, I've shown it there. That's the free bending moment from there to there. But you have to subtract WL over 8 from that. So if you've got a quarter minus an eighth, this will also be WL over 8. That area of that diagram there. This there is WL over 8, just as that is WL over 8. So if you work out these two areas now, just up to the center line there, this area there, the negative moment there, you have WL over 8, WL over 8, times L over 4, because it's a quarter through symmetry, times a half is the area of that. And this A2 happens to be the same area. And you can draw it up accurately and calculate it. You'll see that what I'm saying is quite correct. Now the first moment of area of the bending moment diagram about A, to find delta at C, the deflection at C, what we have to do is we have to subtract these bending moment areas from each other. So we have to subtract the negative from the positive moment. And the moment of A2, which is this area there, is WL squared over 64, going back there, WL squared over 64, which is that dimension there, times L over 4, times 2/3 of the distance, 2/3 of this distance of L over 4, plus L over 4. You're looking for the dimension from there to there. So 2/3 of L over 4 is the distance from there to there, plus L over 4. So the total distance is given here, 2/3 times L over 4, plus a quarter of L. That's the total distance. Minus the first moment of area of A1, this moment area A1, which is the area, WL squared over 64 is worked out up there, times 1/3 of L over 4, because the distance to the centroid of that triangle is 1/3 of L over 4. 1/3 of L over 4. And when you solve both of those, you're going to find that you've got, for A1, you have 5WL cubed over 768 minus WL cubed over 768 for A1. Doing the simple arithmetic on these, you left with a deflection of WL cubed over 192. And of course you could transpose and put your EI. So WL cubed over 192 EI. There we have it. That is the actual deflection for a simply supported beam with a central point load, the deflection at the center of the beam. So pressing on now, because we've got more work to do on this, we work out the moment of inertia in terms of D. We don't know what D is, but we do know that the breadth of the beam is 1/3 of the depth. There we go. The breadth of the beam is 1/3 of the depth. So we can call the breadth 1/3 D times D cubed over 12, which leaves us with an inertia of D to the 4th divided by 36. We don't know what D is. That's what we're looking for. Now, the allowable deflection as given to you in the question was the span of the beam, which it's a 5-meter span divided by 330. That is the allowable deflection. It can't deflect more than that. And so solving that, writing the span divided by 330, you get a deflection of 15 millimeters. We can now substitute that in equation 1. We're going to put deflection of 15 millimeters in there. So substituting, we have 15 times W times L cubed over 192 EI, I being D to the 4th over 64. Doing the arithmetic on this, which I'm sure you're all quite capable of doing, we find that D is the 4th root of that calculation, of this calculation here, by transposing, putting the d to the fourth up there, taking the 36 to the top in transposing this. So d actually works out to be 159.74 millimeters. So that timber beam then, the timber beam, that's what we're analyzing here, this works out to be 159.74 millimeters, and we can round that off to say 160 millimeters. That's more practical, okay? And what did we say that the breadth was? The breadth was a third of the depth. So this is 0.33 times 160, which close enough is 55 millimeters. So the beam that you can use to get the deflection that's been stipulated is 160 deep by 55 millimeters wide. So there, I don't think it was too painful, was it? A little bit more painful than the usual, but not terribly painful. So moving on then to question number 3. Gee, they higgledy-piggledy, aren't they? I hope you're not going to be angry about that. It's just a question of looking at the different problems. And the question for number 3 is a 310 UB, universal beam 46.2, simply supported, carries a central point load of 100 kilonewtons on a span of 7 meters. Calculate the maximum deflection. This one should be easy for you by now, because you know how to work out this deflection from first principles for a simply supported beam with a central point load. The deflection is delta equals WL cubed over 48 EI. You look up, or you're given, in this particular case, you're given E and you're given the I for that particular beam. You plug them into this formula and you get a deflection of 34 millimeters. Okay. And you can actually find out what that is as a span depth deflection and see if it would be adequate or suitable, depending on what's stipulated in the code for steel. Question number 7. A 700 welded beam, 115 kilograms per meter, spans 5 meters and carries a point load of 800 kilonewtons. Calculate the deflection. Now, a welded beam, as I've probably mentioned before, is made up of 3 steel plates welded together. Once you get over, I think it's about 600 millimeters in depth, you have to go to fabricated girders. And this is a 700 welded beam. You can get rolled sections up to about 600, I think, but that's a 700, and it's welded over there. And that will also appear in your one steel tables. So this is what we're faced with here. We've been given the moment of inertia for it, or you can look it up in your tables. 1,150 times 10 to the 6 millimeters to the fourth. The E, 210 newtons per square millimeter, 210,000 newtons per square millimeter. The deflection you're familiar with now, we've worked that out previously. I would do it again for the practice. And we can then plug the loadings in. Our loading is 800 times 10 cubed to bring your 800 kilonewtons to newtons. Span is 5 meters, 5,000 cubed. 48 is a constant times your Young's modulus or elastic modulus times I, and you find that it will deflect 8.6 millimeters. So that's an interesting thing to think about. 8,000 kilonewtons, 800 kilonewtons rather, spanning 5 meters with a central point load. The beam will sag or deflect about 8.6 millimeters in the center. So I think there's only one more problem left, which brings us to the final question, question number 8. A cantilever A 410 UB 53.7 kilograms per meter is used as a cantilever of length L. If the bending stress is limited to 200 newtons per square millimeter, what point load can the beam carry? Using this load, what will the maximum deflection be? So we're tying everything together here by using the bending stress, and from that we can actually work out what the deflection is once we've computed the loading. This would be given to you in an exam, but by now you should be able to look it up yourself actually and see what the moment of inertia is, the section modulus. E for steel, we're using 210 in this particular case, and the allowable bending stress is 200. So the first thing we've got to work out is what the moment is. The moment is purely W times the span, WL, W times 3000 millimeters. We'll call that equation 1. But M, as you all know, also equals Fz, the allowable bending stress times the section modulus. So using that as characteristics, moment equals the stress, 200 newtons per square millimeter, times the section modulus, 933 times 10 millimeters cubed. So the allowable moment that you can put on there due to a bending stress of 200 newtons per square millimeter is 186.6 kilonewton meters. So if we go back to equation 1 now, solving for W, we have M over 3000, transposing this formula, and the moment being 186.6 times 10 to the 6 to bring it to Newton millimeters, divided by the span of the cantilever, 3000 millimeters, gives us a load of 62,200 newtons, or 62.2 kilonewtons is the load you can put on the end of this cantilever and not exceed a bending stress in the material at this point of 200 newtons per square millimeter. Now, the standard formula for this cantilever, as we've mentioned previously in the lecture and this tutorial, is WL cubed over 3EI. So putting into this equation the information you have, W, 62.2 kilonewtons by 10 to the power of 3 to bring it to newtons. Span is 3000 millimeters cubed. 3 is a constant, E and I. And from that, when you solve all that, you'll find that the deflection with that load of 62.2 kilonewtons gives you a deflection of 14.2 millimeters, which isn't a lot, because if you look at 14.2 millimeters, it's only something like that. Okay. Right, thanks very much.